Just a quick outline of what we're going to do. I want to talk to you about the hardware trends that are going on and the CFD usage trends. This is really about, I'll tell you more about this in a second. And then I'll go through some solutions for the issues that we're having, mainly with data I/O in relationship to being able to do the type of post-processing our customers want to do. First, a little bit about our company. We were formed about 32 years ago by a couple of folks from Boeing, refugees from Boeing during one of the layoffs. And for the first 15 years, we were primarily a CFD company. So we spent a lot of time developing CFD codes. And that's our background. We're fluid dynamicists at heart for the most part. Since then, we focused on post-processing, and we developed our own visualization software because essentially we were too cheap to buy SGI machines that were used primarily for CFD post-processing at that time, and that's become our primary business. We have about 40,000 users worldwide. 60% of them are domestic. And we've spent a lot of times over the last 3 years actually working with our customers, focus groups, and customer advisory councils, and really traveling out all over the world trying to understand where they are now in terms of their post-processing needs. And so part of that I'll share with you today. The other thing is, back up. We have an ongoing performance initiative. Now, 15 years ago, we justifiably had a reputation for being slow compared to the competition. Over the last, since then, we've had this ongoing performance initiative, and we are where we've improved our speed by orders of magnitude. And we're now comparable to, according to our customers, we're now comparable to the competition in performance. And going forward, we intend to actually have another order of magnitude improvement in speed. So what's the redshift? I probably shouldn't have used the term redshift because it's not well defined, but what I mean really is just the difference in performance between the CPU cores and the components feeding data to it, all the way back to the storage system. There's been some mention of this earlier already. Now, the key thing for us is that this difference is actually broadening. It's increasing over time, according to the data. So the hardware trends, everyone knows Moore's Law. Components growing with the number of doubling every 18 months. The second, now I say here supercomputer performance is tracking with Moore's Law. Based on comments earlier, maybe I should say theoretical supercomputer performance is tracking with Moore's Law. But basically, this is driving a lot of the work in CFD. The second aspect, going all the way back down to the storage system, and actually the underlying hardware on the storage system, is the hard disk. And this is Kreider's law. Kreider's law actually is that the hard disk capacity is doubling roughly every 12 months. But in fact, the disk read access from the hard disk, I'm talking about at the hard disk level, not through the caches, is only doubling every 36 months. The result of this is a disparity with Moore's Law, and that's what I was talking about. This increasing gap over time. So the CFD data set size is growing with Moore's Law. This is something we've been tracking for some time. It's true. We heard people talking earlier about doubling. Basically, you run the case that you can run overnight. Those are your largest cases you typically run. And the question is why. I occasionally get this why. Why can't we just set at 100 million cells or 200 million cells or whatever the number of the size of grid is that you're you're trying to do. And the reason is really related to this large disparity in length scales that occur in fluid dynamic problems, especially large-scale fluid dynamic problems. And so this is a picture outside of, through a window of a 737. And we're looking at a nacelle. So this is the jet engine, and the intake is here. And you have this little thing on the side that's called a fence, or a strake, or there's various names for it. You'll notice if you fly in various Boeing planes that this is really on pretty much all of them, and it's actually on other planes from other manufacturers as well. And it plays a key role in the behavior of the wing, the aerodynamics over the wing. In particular, you can see here, what it does is it creates this vortex that comes off of the fence, and it goes over the top, and it energizes the air that would otherwise be blocked by the nacelle. The nacelle, this thing is like a big cylinder sitting out in front of the wing when it's coming in for landing at high angle of attack. And this energizes the air and helps keep the flow attached over the wing. Without this, the airplane stalls at a lower angle of attack. The wing stalls, and you have to actually land at a higher speed or have a longer wing or some other, or play games with the geometry of the wing, the twist, for instance, to make it work. And so the one thing you'll notice about this vortex is very small relative to the size of the wing. And it's not just one-dimensional like the boundary layer, which is right on the wing, where you can actually stretch your grid down to the wall. It is actually two-dimensional in the sense you have to stretch grid in two directions, and it interacts with the boundary layer. The net result is, I'll show you some results later of the 200 million cell cases, and I can tell you right now that 200 million cells cannot capture this vortex. And remember that this is key to the aerodynamics of the plane. So if 200 million cells cannot capture this vortex and it's key to the aerodynamics of the plane, well then you're going to keep growing the data set size as performance goes up. And this is going to continue for quite a while, in my estimation, at least through 1 billion cells, probably through 5-6 billion cells for this type of configuration. So wide range in length scales, and resolution of the grid is constrained by computer performance at this time. How long it takes to run, how much grid you can run overnight. The second thing that is driving the usage in CFD for on high performance computers and actually data set size is parametric CFD analysis. This is all tied up in optimization ultimately. And also robust optimization, uncertainty quantification, development of various statistical models via, we've heard about this before, Gaussian processes and Monte Carlo techniques to actually develop an understanding not only of the performance of the aircraft, but also the performance over a not only, but also the uncertainty in the performance and the design. Some of the things that you do is the simplest would be just aero-based database development. This is for follow-on analysis primarily, say for a flight simulator, so that the flight simulator can accurately portray the behavior of the airplane. Also, optimization, robust engineering. I mentioned that briefly. And verification, validation comes into this too. So you're actually pulling experimental data in as well. And a lot of our customers are now incorporating both of these into using the experimental data to actually calibrate their statistical models that were originally developed using simulation. So you have the simulation-driven design, and then you have experimental data to calibrate the statistical models. The net result of this is you have a lot of CFD runs that you're generating, hundreds or even thousands, tens of thousands maybe. I asked a person at a large airframe manufacturer not long ago, what he considered to be a large number of dimensions in this design space. And I was expecting something on the tens to the hundreds range, and he said thousands, that they actually deal with thousands of dimensions. Now, they don't necessarily deal with those simultaneously, but those come into play in the final analysis. And in the end, you need to analyze these simultaneously. At some level, you need to analyze these simultaneously because they are being used simultaneously to actually develop the statistical model of the behavior of the system. So this is what we're calling simulation analytics. If you will, it's kind of the marriage of the big data stuff, which is highly unstructured data, with the engineering data, which is we're highly structured and actually based primarily on equations we know. And we generated this data, the simulation data, based on equations we know. So those are the drivers. We've been ongoing developing a simulation analytics tool, and this gives you an idea of what we're trying to accomplish here. So we're a visualization company at heart, so we do a lot of visualization. Underlying most of this is some statistical models, some surrogate modeling. But in the end, if you need to do an understanding, a root cause analysis of what is going on with your design, you need to go back to the underlying data. And herein lies a lot of the problem with the data access, because now instead of dealing with a large, say 500 million cell CFD case, you're dealing with hundreds or thousands of 500 million cell CFD cases. And you need to selectively be diving into each of those cases to be pulling out information that you can then use in this sort of analysis where you can actually do it, be comparing the results over these sets of cases to understand the root cause of a certain behavior you're seeing in your statistical models. So, operations over enormous amounts of data, as I just mentioned, and in the end, all of this becomes a huge issue for the large data performance. It's not just one case now, it's many cases. This is just a really simple look at the data processing pipeline. Now, we're primarily a post-processing company, so we're dealing with data that's been generated at the large scale computing facilities. And as I mentioned, you have this disparity. This is Moore's law. The performance here is doubling about every 18 months, whereas the ability to pull the data off in these huge amounts ultimately is driven by the underlying performance of the hard disk. Now this is an individual hard disk. Obviously, you're dealing with parallel file systems, but we'll discuss that in a second. So but that's the ultimate problem is this disparity, and if you do an analysis and you assume that, in this case, we're dealing with a simple like workstation like hard disk drive, and you look at the time it takes to actually read the data off the hard disk, it looks something like this. It's actually growing over time, and this is because even though the performance is improving over time, remember the data set size is growing with Moore's law, and the performance of the hard disk system is not growing with Moore's law. Not as fast anyway. So the time it takes to read the data is growing over time. The time it takes to transfer the data over the network is, I show it declining here. It may actually be growing. It depends. There's a wide disparity in networks. In any case, it kind of grows in huge chunks, order of magnitude type chunks. And then in the end, you end up with this sort of, combine it all together and you end up with this minimum in processing time that occurs, in this case, somewhere between 2004 and 2010. That implies it's already happened. So if you're doing your analysis on a workstation, even though the performance of the computer is getting better and the performance of the hard disks are getting better, the time it actually takes to do the analysis is getting longer, and it's because of because of the disparity, the redshift. So ideas for overcoming it. I mentioned the hardware-based stuff. The fact is, I'm sure there's people in the room that know way more about this than I. But I will mention the first one is the parallel file systems, which is essentially adding spindles, right? You know, if one isn't good enough, you do 100 of them, and now you can, in theory, maybe be 100 times faster as you stripe your data across those systems. The issue with that, like I said, I'm not an expert at those systems, but in the end, you can't outgrow a geometric process. You can't outgrow an exponential growth process with an additive process, right? These things this is doubling every 3 to 4 years, this gap between the two. And it can't be, you can't just add more things and get overcome that, right? Comes back to the old joke about the guy who said I would, it was getting paid, and he said, how much do you want to be paid? And he said, today I want a penny, but tomorrow I want you to double it, 2 pennies, the day after that, 4 pennies, etc. And by the end of 2 months, he had more than the gross national product of the world. You know, it's growing. If it's growing exponentially, it's very difficult to keep up with. So you need something that can handle that. And then there's new types of storage systems. I'm hoping to learn more about that in the next 2 days. I won't actually talk about that anymore here. The in situ visualization is another approach. You don't even write the data to the disk. This works well if you know exactly what you want to look at. But we're talking about the simulation analytics approach, and we're talking about doing root cause analysis. And in those cases, you don't know what you need to look at until after you've developed the statistical model, and you need to go back because you don't understand something. And if you need to run all 100 or 1,000 of your cases, CFD cases again, that's a very difficult problem. Parallel visualization does solve some of this. It allows you to actually do independent reads. But again, it doesn't entirely overcome it, in my opinion. Ultimately, what you need to do is reduce the amount of data you read from the disk. And remember, we're doing the same sort of operation with the simulation analytics over a broad number of cases. And so in those cases, what you want to do is be very selective about how you read the data from the storage system. And you need to do it in a way that scales sublinearly with the size of the grid. Significantly sublinearly if you can. So the approach that we're taking, and there's many ways of skinning this cat, but the approach we're taking is on the large volume files, you save an index file and you load only the data you need. We're not the first people to do this. This is based on a lot of work done on the out-of-core algorithms in the 90s. Also, there's some work at NASA Ames in this area. And in that way, you can actually dramatically reduce the amount of data you read. This is what we're, a really simple example of how this works. So this is a grid, and this is, obviously you don't do this in 2 dimensions, but imagine you wanted to. This is your grid, and this is an ISO line, contour line you want to extract. You break up your grid into pieces. You do some indexing on the pieces so you can rapidly determine which ones you need. These are the ones you need, and you can see it's only 5/16 of the total data. You don't even read the stuff in the, that is shaded. You only read the stuff that's white. Same sort of thing can be done in 3 dimensions. This thing that looks fuzzy here is actually the subzones. These are the subdomains, and it works for finite element data as well. I don't want to go too much into those details, but basically we use an interval tree and sometimes KD interval trees and various other tree-like structures to help us to quickly access which subzones we need to load. Again, this is nothing new. This has been done since the 90s at the very least. But just to give you some performance numbers, 10 billion cells, you can query the tree in 1.4 milliseconds, so it's very fast. And the tree size is substantial, but remember this is 10 million cells, so it's a small fraction of the total number of cells. So I'm going to pick up speed a little bit here. I'm going to go through a few cases to just show you how this works. So quickly, for a simple case looking at size of grid, just to show you that with this we can actually scale quite a bit sublinearly. The sort of the theoretical optimum for an isosurface is 2/3 n to the 2/3, where n is the total number of cells, and we're right there. And then with stream lines, it's actually more like n to the 1/3, so it's even faster. So this is the transport aircraft I told you about earlier. It's a full aircraft configuration. It's in landing configuration. Has flaps down, slats down, landing gear. It's roughly 200 million cells. And if you look at a slice at x equals 0 position, x equals 25, actually look at slices from front to back. X equals 25 is a very fine grid region because it runs right through the nacelle, and there's actually grid inside the nacelle, and it runs through the flaps. And you get something like this where you're talking seconds now to read and generate the data, generate the slices from the file. It's between about 10 seconds and 2 seconds, depending on the complexity. Similarly, well, this gives you a comparison to the standard Tecplot, which reads a much larger portion of the data. And the ratios are between 20 and about 140. So an order of magnitude to 2 orders of magnitude faster. It's also true in memory. So this is the memory. It's less than a gigabyte. So this is 200 million cells, but we're using less than a gigabyte of memory, and the ratios are similar. Oops, let me go back one. The key to the memory is that we're trying to pull in hundreds of cases in the simulation analytics for the comparisons. And so you need to have a very small memory footprint for each case. And that's what we're doing is with this. The second thing is, well, it also works for stream traces. I'm going to speed up quite a bit here. We've also done this with a wind turbine. Similar results, not quite as dramatic in this case because this has a large number of zones and we haven't optimized for that yet. Another case with the flaps and slats down. And so I'm going to scoot forward to the conclusions. So we've gotten a dramatic reduction in memory requirements, factor of 4 to 50. And scaling is order n to the 2/3 to n to the 1/3 for the streamlines. And we also get significant improvements in speed. Orders of magnitude improvement in speed on the large single zone cases, not quite as substantial when it's broken up initially. And this isn't just for the hard disks, right? This same thing will benefit memory, network bandwidths, and all the way up through the chain of components feeding the cores. The downside of this is you need to actually change your file format. So this is a non-trivial thing for a lot of people. But in the end, somehow you need to get the full benefits of this change, you need to have your file divided up into pieces that are small enough that it can be indexed. And at that, I'll take questions.
Thank you, Scott. Oh.
I
turned this one. They turned that one off. According to the clock, we still have 1 minute and 44 seconds, 43. Are there any questions, realizing that the next thing is the break? Go ahead, Mike.
What do you mean by redshift? What do you mean by redshift? As this appeared to be an astrophysics session, I was expecting something else.
I regretted using that shortly after I put it on there, and so it's because it's a buzzword. But it's commonly used. For instance, a couple of years ago at supercomputing, everyone was talking about the redshift being the discrepancy in performance between the components feeding data to the cores, to your compute units, and the actual performance of the compute unit. And it implies that these things are separating, right, as they do in the redshift in UV or in radiation, right?